In class, today we're going to talk about the law of conservation of energy. So let's jump right in. The law of conservation of energy is that energy can neither be created nor destroyed, simply transformed from one form into another. What this means in more English language terms is that the total energy in a closed system will never change. Or as a simple formula, total initial energy will equal the total final energy. So let's look at a situation of the energy of a ball that's being thrown into the air. And we're going to ignore air resistance for our first little scenario here. So here's a ball, and it's thrown into the air, and it goes up, 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 up. And we're going to look at it over here. Comes down, we're going to look at it here. And then we're going to look at it as it lands back at the same height that it was thrown from. Well, there are two types of energy that we said we'd be focusing on. We said we'd be focusing on kinetic energy. So there we can look at the kinetic energy at each moment in time. But we also said that we would be looking at the potential energy. And in this case, the potential energy is given by gravitation. So this is the potential gravitational energy. And just as a little reminder, our kinetic energy can be determined by taking 1/2 multiplied by the mass multiplied by the square of the velocity. And the potential gravitational energy in this case can be taken by taking the mass multiplied by the acceleration due to gravity multiplied by the height that it has achieved. Now, let's give an initial amount of kinetic energy. When you start throwing the ball, it is moving. So let's say, just for the sake of argument, that there are 7 joules of kinetic energy that it begins with. Now, how much potential energy does it have at the very beginning? Well, if we consider this our starting height, it has not risen at all, so it has no height. That's one way of thinking about it. And if it has no height, that means it has 0 joules of energy. Now, when the ball goes up and up and up, it'll reach the peak of its flight. And we know something that happens. When something reaches the peak of its flight, it stops moving for a brief moment. If it stops moving, that means the kinetic energy has to be 0 joules. Well, according to the law of conservation of energy, what does that mean about our potential energy? The total amount of energy has to be the same. So in our first situation, there were 7 joules and 0 joules. So that's a total of 7 joules. It means that in our second situation at the peak, there has to be a total of 7 joules as well. There's got to be 7 joules of potential energy. That kinetic energy has turned into potential gravitational energy. And now the gravity has energy to pull it back down. And hopefully that actually matches what we would expect. Halfway down, it would be half the height. So half the height would have half of the potential energy. What does this mean about my kinetic energy? If you said it also has to be 3.5, so it reaches a total of 7, you would be correct. And lastly, as the ball is reaching the initial height that it was, again, the height is now at 0, which means there are 0 joules of potential energy. What is happening to the kinetic energy here? The kinetic energy is, again, 7 joules. And this actually matches our understanding that parabolic motions will have symmetrical velocities at the same height, right? They have the same amount of kinetic energy, meaning the velocity is the exact same in size. So this understanding of the total is always 7 also is matched by our understanding of symmetry in kinematics and everything else that we've learned so far. Hopefully we can see how that energy can transform into one type and another, but we always see that there is a total of 7 joules of energy. Does this situation look any different if there was air resistance? Let's try this out. Here's a person again, and they're going to be throwing this ball, and it's going to head upward, and then it's going to reach the peak, and it's going to head down, and then it's going to head down to the same height that they threw it. What happens when we do have friction? Well, kinetic energy is still a thing, and potential energy still exists. But what does friction do? Now, if you're wondering, well, what sort of energy does friction make? The easiest thing to do is to take your hands, put them together, and rub them. When you rub your hands together, what do you feel? You feel your hands warming up, right? It seems that friction provides thermal energy. Now let's start with the same situation. 7 joules of kinetic energy, 0 joules of potential energy. When you begin, when this ball has just begun to move, has it encountered any air and has it encountered any friction yet? The answer is no. There's been no friction, so there would be no energy lost due to friction just at the beginning of the motion. But by the time that it reaches the very top, it has definitely encountered some air resistance. It's encountered some friction. Perhaps it's encountered 2 joules of energy. What does this mean? It means that our potential energy total, according to the law of conservation of energy, has to be 5 joules. That means when there's friction, a ball that you throw won't go as high. What happens when it's halfway down? Well, halfway down has half of the potential energy, but this thermal energy is going to continue to grow. What is our kinetic energy going to be this time? It's going to be 1.5 joules. Because what does our total always have to be? Hopefully you said 7. And when it gets to the very bottom, there's no more potential energy, and our thermal energy has increased just a little bit more. What does this mean about our kinetic energy? Only 3 joules. As before, we see the total energy is 7. And our law of conservation stays put. But what does friction do? It seems that friction takes away kinetic energy and transforms it into thermal energy. And so long as you consider the transformation into thermal energy, friction can be part of your closed system. Our big rule here, however, is the total energy should never change throughout this situation. Energy is conserved. Let's look at a situation. Roller coaster problems are classic problems. These are ones that we use all the time. So we're going to start with a roller coaster that goes whee like this. It's going to be here. Going to start maybe 80 meters high. It's one heck of a roller coaster. Point B is going to be here at the very bottom, and point C is going to be here 40 meters up. So here's point A. And let's say at point A, this cart is going to be at rest. It's going to be just enough for it to begin rolling down, but we're going to start it at rest. Let's also give this cart a mass of 10 kilograms. So using the law of conservation of energy, we should be able to determine the velocity at point B and the velocity of point C. Let's go ahead and try this out. Here's the thing, is we know information about point A, don't we? So we're going to determine the energy at point A. And then the rule is, the law of conservation of energy says that this has to be equal to the energy at point B. All right. Now we've really been dealing with 2 types of energy. we've been dealing with the kinetic energy, so the kinetic energy at point A, and we've been dealing with the potential gravitational energy, so I'm going to be dealing with the potential energy at point A. And that means that should equal the total energy of B, in other words, the kinetic energy of B and the potential energy of B. And now we can just break these down. Remember, kinetic energy is 1/2 mv squared, and potential energy is m times g times h. So kinetic energy A is 1/2 times that mass of 10 times the velocity of 0 squared, plus our mass, 10, times our acceleration due to gravity, 9.8, times the height, 80. And that should equal the kinetic energy at B, 1/2 times our mass times that unknown velocity of B. But remember, it gets squared. Plus the potential energy at B, the mass, times 9.8 times, what's the height of B? It's 0. Anything times 0 is 0. So that means these two numbers we get to ignore. And we can go ahead and use our calculator to solve this. And we see that the velocity of B is 39.6 meters per second. The cart is going really fast at point B. Now at point C is which energy should we take? Should we take the energy at A or should we take the energy at B? Which one should compare to the energy at C? And the answer is either one. Either one would work, because if you consider, if the total energy doesn't change, the total energy at A should be exactly the same as the total energy at B, in which case it doesn't matter which one you choose. I would choose A because I would have no rounding errors, but if you chose B, you'd end up getting the same result. So I recommend you take a moment to go ahead and try this problem on your own. The final answer is 28 meters per second. I've given you the answer, but I want you to try to solve this problem on your own and just use this as the answer key. That's going to be all for our law of conservation of energy right now. This concept and the way that we use it to solve, however, is very important. All right, that's all for today. Have a good day.